So for this lab, we took two different lenses. We have this lens, which is pretty much normal, and then we got this fisheye lens, which is already on this camera. And then we took this plane right here with all these checkerboards, and we tilted it in random directions, up, down, side to side, a combination of those. And what our software later on is going to do is try to fit the geometry of our images to one of these planes, so that way it can remove the distortion from the different lenses.
Seen here are results for the field of view tests. We took pictures of a ruler in both the horizontal and vertical directions for both the fisheye and normal lenses. We then used trigonometry to compute what the vertical and horizontal fields of view were for each lens. So in treating this camera as a pinhole camera, we have our object coordinates here, which are homogeneous. We multiply them by our camera projection matrix to give us homogeneous image coordinates, which then we convert into Cartesian coordinates. We then have to convert the image coordinates from millimeters to pixels. When we do that, we get our U and our V. Inside, you can see our scaling factors for our pixels. We can see our focal lengths in pixels, and then we can also see our skew factor, which has to do with non-rectangular pixels. The equations for the U and V can be represented in matrix form, which you see here. So now when we add distortion into the mix, our X and Y are no longer X and Y, but now they're XD and YD, which take into account the ray error in both the X and Y direction. Since we're dealing with third order radial distortion approximation, we get these terms here with a K1 and an R squared. That K1 is our distortion coefficient, that R is our normalized field height. We then use this conversion from the homogeneous into the Cartesian coordinates, and we plug that in back into the U and the V, but this time using XD and YD, and then we get these equations for U and V with distortion. So in doing these calculations, we have to take into account that the coordinate system for the object points as defined by the scene and the coordinate systems for the object points as defined by the camera are different. So in order to change between the two, we need a transformation matrix to get that change of base. This transformation matrix is seen here, whereas these first three columns correspond to the X, Y, and Z of those reference grids that we take pictures of in the lab. And then the position of that grid corresponds to this last column here. As we can see, this transformation matrix is extremely important due to this equation here, which was shown and illustrated previously. Here's an example of how the software works. Once we load all the images, we can then go ahead and extract the grid corners. So for each image, we take 1, 2, 3, and 4 corners. The software then automatically fits it using a distortion coefficient. This coefficient can be manually changed in order to receive a satisfactory fit. So once all of the corners have been extracted, we get this figure here. We can then go ahead and run the calibration, and we get all the parameters here. We can then display the extrinsic parameters using this option here, as well as the error analysis. These are the results. For the normal lens, here are the calibration results. These are the extrinsic parameters, and this is the projection error. The distortion model suggests that radial distortion dominates in this case. This is an example of a distortion correction. For the fisheye lens, these are the calibration results. This is the projection error, and this is the extrinsic parameters. The distortion model once again suggests that radial distortion dominates in this case as well. This is one of two examples of distortion removal. You can see the distortion is removed very nicely here. And here's another example.
So for the next part of the lab, what we did for both of those lenses is we put the corner facing towards the camera, and then once we have that, the camera takes this image, and using those planes that we did with the checkerboard before, we can fit these to those different planes, and it basically creates 3D planes, and then from that we can measure the angle in between these two surfaces.
So we first fit the left side of this box to get the rotation matrix, followed by the right side to get that rotation matrix. Then using linear algebra, we can get the angle in between to be about 89.3 degrees.
This is an MTF chart image with a low distortion lens. The 5 different black regions are represented here with the 5 different MTF plots. So you can see that for the low distortion lens, they're all relatively equal and have a similar shape and cutoff. For the high distortion lens, the 5 different regions, as imaged here, show different MTFs, which vary depending on the placement they are in the image space. The lighting and the creases on the paper can affect the outcome.